so we'll get started. Nicole, if you can hear me, I'll try to keep an eye on the chat. It might be a bit difficult, but feel free to pop any questions you've got in there. This is hopefully going up on YouTube, so maybe somebody will use it at some point. Currently, I'm connected to an empty room, but you know what? That's how we do it. Okay, so we'll get started to the first question. So we've got an object which has zero acceleration over an extended period of time. The way I kind of like to think about this question is rather than approaching it from maybe a math sort of point of view using like a delta V over delta T. Let's not really approach it like that. Let's just kind of think about it in reality. So if we just have some block sitting, we know, you can think about a car, accelerating is moving faster or changing direction when we take a physics approach to it, sort of thing. So if it's got zero acceleration, it might have zero velocity, but it not necessarily must have zero velocity. So maybe that one could be right. We'll leave that for the moment. Its velocity must be unmeasurable. That's not really going to be true. We can always measure the velocity when, especially if it's not accelerating, it's even easier. It might have a constant velocity. That's so we put a circle around the first through, and no such object can possibly exist. That's certainly not true. So basically the way you're going to approach this one is just think about your two plausible answers, and for something to have a constant velocity, that velocity could be equal to zero, which is totally plausible. If we wanted to use the maths, we can think about the top of this being zero because there's no change in velocity, so therefore we have zero acceleration, which is what we want. So it might have zero velocity, that's certainly true, but a constant velocity is a better answer. So it's going to be part 3. All right, cool. So the next question, we've got another moving object. So now it's got a constant non-zero acceleration in the negative y direction. So we can imagine that like gravity, and an increasing acceleration in the positive x direction. So maybe it's friction or a car or something like that. It's accelerating from a car. So we're going to choose the graph below, which best describes the object's y position. So I know it says x over here, but we'll just imagine it says y, and imagine this one says y. Cool. So told us we've got a constant acceleration in the negative y direction. So if we've got a constant acceleration, it means it's kind of going to have like a parabolic, a squared function for its displacement, which is what we're looking at here. So it tells us we've got an acceleration, but the graph is a function of its displacement, of its distance, basically. And so since it's constant and non-zero, we know it's going to accelerate, so its displacement is going to go in like a parabolic motion. So it's not going to be this flat one. This is a constant displacement, which means we have a sort of linear velocity. Let's say over here, yeah, we've got this. So basically this is going to be our right answer because we've got this squared relation. It's not going to be this one because it's going to speed up over time. This one kind of slows down, it's concave down. So that's why we're going to get this one. This red graph is our correct answer. All right, so on to the last question for this one. We've got a race car, which is going around an oval racetrack. The length of the racetrack is 8.78 kilometers, as we said there. What you should always do when you're tackling any question with physics, no matter what physics you're doing, you should always sort of underline or take note of all the data you're given. So we're given the length of the track, which we know is this. That, I don't know why I didn't read, but you've got it there. And it's telling us the first lap, it was taking 7.51 minutes to go around the track. We want the car's average speed. So what I always like to do is I like to circle my data, and then I like to underline what I actually want us to find. So we want the average speed. So average speed, you should have this formula either on your formula sheet or just kind of have it in your head. Average speed is the change in distance divided by the change in time, where this delta just means change in. I'm hoping you guys have seen this at some point. I should be looking at there, I suppose, a bit more. So again, we want to be using SI units. We want to be using meters and seconds, not kilometers and minutes. So we can put 8.78, and to convert from kilometers to meters, we multiply by 10 to the 3. 10 to the 3, and then it's always good to put your units down so we can keep track and make sure we get a plausible answer at the end. So that's our delta L, because it's saying the first lap and we want the average speed over the lap. So the whole distance of that is going to be at 8.78 kilometers, or 8.78 by 10 to the 3 meters. Cool. And our change in time, it tells us 7.51 minutes. To convert from minutes to seconds, you just multiply by 60 seconds. So once you pop that into your calculator, you should get out 19.5 meters per second. Cool. So remember that we want to check our units. So we've got a funky color, we've got meters here and seconds on the bottom of our fraction. So we're going to end up with meters per second, which we should know is our measurement of speed or velocity. Something. Cool. All right, we'll pop on to the next part. I'll just do it over here. Cool. So 3 laps, it was found to take 22.4 minutes. Cool. We want the average velocity. All right, so we're going to basically be using the same thing. So velocity average is equal to the change in displacement over the change in time. Now our change in displacement this time is 3 times our length, which is 8.78 times 10 to the 3, because as we said before, that length is our lap and it's doing 3 laps now. So we've got 3 times the regular length. And we're going to be dividing this by not 3 times t, because it's telling us 3 laps took 22.4 minutes. So just 22.4 minutes multiplied by 60 to get our seconds, giving us our meters per second. And that's going to give us 19.6 meters per second. Always good to take note of units when you get to the end of a question. So it should be an SI units, meters per second, which we've got there for both answers. And also good to take note of your significant figures. We've got 3 significant figures here and 3 significant figures here. And we've got 3 on our questions. So yes, no questions in the chat. I'm hoping, or you can hear me. Feel free to pop some questions if you've got them. So we'll move on. Okay, so we've got a watermelon being thrown horizontally from the viewing platform of the building, dealing with any projectile motion, which is effectively what this question is. You always want to be drawing a diagram. So we'll start with that. So I just like to draw my building with a height h. So maybe we can pop that in like that with 13.2 meters. The watermelon is thrown vertically with some v equals 1.05 meters per second. And we should put meters there. Great. And you should probably know that it's going to travel like that in a parabolic motion. So this is our velocity and this will be our displacement. We're going to call it x because that's not right. We'll call it s. Displacement. Cool. All right. And we've already popped our data on here, so I'm not going to underline it, but it's worth mentioning, neglecting our resistance, which makes our life a lot simpler. Cool. Calculate the time for the watermelon to hit the ground. So the way we are going to tackle this one, the way you tackle any projectile motion question is you split it into components. So x and y. We'll call x this direction and y this direction. Y that one, x that one. Great. So we'll set our s, y. You've probably got this equation. S is equal to ut plus 1/2 at squared. And since we're dealing with y, it's uy and ay. Remember, time is just what goes across all of them. Cool. And so we want our s at the bottom. So we're going to have also we know. So yeah, we want to calculate the time. we're going to be wanting to use this formula because for a few reasons, we don't know the distance. So we don't know like this distance there. So we can't really use the X displacement version. And we don't know the final velocity. We only know the initial velocity. So that's not really going to help us. So we know they've told us it's thrown horizontally. So if it's thrown horizontally, that means our Ux is going to be equal to 1.05 meters per second. And since horizontally, it's not thrown in the y direction at all. So that's 0. So that basically means this term is just going to be 0. So effectively what we've got is our Sy is equal to 1/2 AYT squared. Cool. And so we know in the time that it takes to hit the ground, which is what's it want us, it's going to travel 13.2 meters down. So minus 13.2 meters is equal to 1/2. And now this is projectile motion. So we know that our acceleration in the y direction is going to be negative g, where g is equal to 9.8 meters per second squared. Negative g times t squared. If you did all the maths for this, you'd end up with t being, what did I get? 1.64 seconds. So a few tricks to note from this question. We've got negative signs. Remember, obviously, that our time is going to have to be square rooted. So we need this to be positive. So that's kind of one way that I use to like check that I'm using the right directions. So you might go, oh, I'll just use negative gravity, and then you'll end up with a negative answer, and that's not going to work. And the reason is because you need to take your displacement in the y direction also in the negative direction. So that's going to get you that negative sign there. So yeah, you could have also just as easily defined y as downwards. So then gravity is, so the acceleration in the y direction is just gravity, and the displacement in the y direction is just gravity. Similarly, you could have defined your 0 point here. There's a few different ways. The point I'm making is just keep track of your negatives and make sure you're aware of where they need to go and you don't have any stray ones. All right, cool. Part B. I'm going to run out of room for this, I suppose. Actually, I should be fine. Part B. The distance from the base of the building where the watermelon's explosive impact will take place. So distance from the base of the building, and assuming the ground is a horizontal plane. So again, projectile motion, we always want to be looking at the diagram we've drawn and what the question is asking us. Distance from the base of the building, so that's this x distance here, and we're assuming the ground is horizontal. Simplifies things, we don't need to worry about angles or anything like that. Cool. So we've dealt with stuff in the y direction. So, and now we're calculating stuff in the x direction. So let's start to use that. So we can use the same formula. We can use Sx is equal to Uxt plus 1/2 Axt squared. Cool. Now we're going to do a similar trick to what we did last time by getting this term to be 0. And we can remember that the whole point of projectile motion is that the only acceleration is in the y direction with gravity. So we don't have anything in the x direction. So this term is going to be equal to 0, which gets this thing probably down to something you know, which is speed is equal to distance over time. This simple relation where this is our speed, this is our distance, and this is our time. So that I can see that, just, you know, always good to relate it to something you guys probably have done before. So we've got this formula. We want to calculate S of X, so we're going to leave that there, and we're going to set that equal to Ux, which remember was given to us over here in the question. So 1.05 meters per second multiplied by time, which is 1.64 seconds, which is what we calculated before, remember. Neatly look, our units are going to cancel off. This is divided by seconds, this is multiplied by seconds, leaving us with a very nice answer of 1.72 meters. Now, again, as I said, end of every question, units and significant figures. We've got our units in the right, meters per second, and we've got 3 significant figures, which is what we've got both our answers. So I'm pretty happy with that one and happy to move on. Any questions? Oh, the camera moves. Look at that. Look at that. I'm going over here. Yeah. Okay. I'm moving pretty quickly just because there's a fair bit to cover. I'll take a brief break and 12 and anyway. No one thinks I'm really talking to myself. All right. An object is observed to sit at rest. So we've got another thing. Instead of accelerating, we've got something sitting at rest. So its displacement is 0. It's not moving. Which of the following statements about the object is true? Sorry. Yeah, it's not its displacement is 0. Its velocity is 0. Its displacement is whatever we want it to be. Its velocity is 0. So when it has 0 velocity, it must have 0 net force acting on it. So we need to remember our sort of equilibrium things, that if the net forces cancel out, we've got our sum of our forces equal to mass times acceleration. So if the sum of our forces is equal to 0, we'll have no acceleration. And no acceleration, as we discussed in the previous question, no acceleration doesn't mean 0 velocity. It means a constant velocity. So that's, again, our problem with this is this little word here, must. Whenever if an object has 0 velocity, it does have 0 net force acting on it, but it could have a constant velocity and it still has a net force acting on it. So the first part isn't 100% correct. The object's velocity does not change, so the forces acting on it must be 0. That's probably a little bit more correct, but let's read through the rest of the answers to make sure we're happy with that one. The inertia of the object is preventing it from moving. So remember, inertia is objects in motion stay in motion, and objects at rest stay at rest unless acted on them by another force. So that's not really correct. And then the last point is non-conservative forces must be stopping the object from moving. Non-conservative forces are like friction, air resistance, that sort of stuff. And that's not stopping it from moving. It's just not, like we stand in one spot and we don't move, not because of friction or air resistance. We move because there's no forces acting on us. So it's going to be B. Reminder that the object's velocity could be 0. But the more important point is that it's constant. It's not changing, because that's our definition of acceleration, is our change in V over our change in time. These questions are always really tricky. I struggled them when I was going through 1A. So it's just important to check all your answers, like look at all the answers for the multiple choice, try apply it to a real life situation, and then go from there. Cool. Now we've got circular motion. Which is another type of motion we deal with. We've got sort of just generic motion like this. We've got our projectile motion like this stuff, and we've got our circular motion. So circular motion. There are plenty of different things that can be said about it. We'll just tackle this one. So we've got something undergoing circular motion, and we need to figure out what's not true in this case. So we know when things are undergoing circular motion, there has to be a force and therefore an acceleration. And that's always towards the center of the circle. That's what actually, keeps it moving in a circle, that centripetal acceleration. So the net force must have a constant magnitude and changing direction. I just said that the direction is always towards the center of the circle. So that one already, we can probably cross that off and saying that's not true. So therefore that's our right answer. But let's just check the rest of them to make sure. So the net force must have a constant magnitude and be directed radially inwards. That's the way we defined our circular motion. So that's correct, pretty sure. So we'll leave that. The body is subject to a constant force. This is true. We can sort of prove it by looking at the formula, mv squared on r. This is our centripetal force. The mass of our object isn't changing. The radius shouldn't be changing, and the velocity shouldn't be changing. So therefore, this is just going to be a constant value, some number. So this one's correct, this one's correct, and it's undergoing centripetal acceleration. That's what we define again for circular motion. So therefore, A is the only one incorrect, and A is our answer. The trick is, remember, for centripetal forces and centripetal acceleration always towards the center of the circle, always at a constant magnitude. Cool. All right. Now, question 2, we've got a toy airplane. Let's do our trick. I'm going to use a sexy highlighter. We've got our mass there. Stop laughing at me, Fletcher. We've got our mass and our length. Remember, always underline our data. Spinning around in our circular motion, just like we had over here. And then it's got a speed of 30.5 kilometers per hour. Now, the first thing that's popping out to me without even reading the question is we're going to have to do something with this because we don't like kilometers per hour. That's lovely. I don't know what that sound is. We want to be dealing with meters per second. So let's deal with that when we get to it. The period of circular motion. So remember that period is the time taken for one complete traversal of our circle. And we have a formula that we like to use. That formula is give me one sec.
Did you enjoy my addition to your Zoom call? Perhaps. What was the addition? Right? Yeah. I was just gonna say that they put like popping on. Yeah. I don't know. We tested it inappropriately. I'm gonna report it.
Sorry, I did this question wrong. I was reading this one wrong. Sorry. The forces acting on it must be 0. This isn't true. We need our net force to be 0. So it actually is.
Oh, do they not see your face in the report?
No, I can see my face.
Oh, okay, so then they did see mine. Oh, I already saw it.
Huh? Yeah. Yeah, it stops.
What was it doing?
It was just popping. It's a bit weird. Like the projector at the back, just making weird noises.
Yeah.
I'm really enjoying this. Just presenting to no one.
It's lovely. It's not the music?
No, definitely wasn't.
Okay. The music's gone high. Also, the contrast is really fucking weird.
Language.
The contrast. Sorry, it's really weird.
Weird, yeah.
My goodness gracious, my apologies.
Nicole, my
Lord heaven and whatever. I don't know. I'm not good at something.
Why are you interrupting our study session? This is going on YouTube.
I think that I'm already on YouTube.
Is he?
No.
So V is equal to R on T. Get out of my revision session. Yeah, for sure. Okay, this is our formula. The other one involving period is F is equal to 1 on T, but we don't want to use that because that requires working out our frequency track. Not worth it. This is a much nicer formula because we've got all this stuff already. So we'll just rearrange it. T is equal to 2 pi R on V. Now this V is our, what we call linear velocity. So it's the like the tangential velocity, basically. We also have another type of velocity with circular motion, which is our angular velocity. And that is given by, I always forget this, the velocity multiplied by the radius. So we got that, but we're not dealing with it this time. We're just dealing with our other one.
That was very interesting. I was like sat here and I can still see myself on the screen. Because every time we looked over, like we were looking. Adam's on the Zoom call, right? Yeah.
I think so, yeah.
Oh, yeah, I was dancing in the background. That was my addition. I
don't like Adam in the background. He heard how bad I was.
Why? It's fine. You're the worst demonstrator.
Sorry, it's me. Was on the go. That's what we've got. That's our angular velocity. Cool. So, but we're not dealing with that. We're just dealing with our tangential velocity. So we've got our radius. So our there. Our period is 2 pi. Our radius is given to us as 32.4 meters. Cool. And then divided by our velocity. So we've got 30.5 kilometers per hour. So to convert the way I do is I convert the top and then divide by the convention, the bottom. So to convert kilometers to meters, we multiply by 10 to the 3, same as before. And then we divide by, to convert hours to minutes, we multiply by 60. And then to hour, and then minutes to second by 60 again. So 60 times 60 seconds. This is in brackets. Cool. So yep, that's going to give us this. Meters is going to cancel here. And then this seconds, because it's divided, is going to come up. So we're going to end up with a nice answer that we like. And the actual value is 24.0 seconds. So remember, significant figures, we've got 3 in the question. So we want to have 3 in our answer. That's why I don't just put 24 seconds, because the actual, if you put it in the calculator, is like 24.03, I think. But we don't want to use that because we want a significant figure. So we keep it as 24.0 seconds. Cool. Next, we've got our tension in the string, holding the airplane in its circular motion. So remember that tension in strings is really just the force. Oh no, our one viewer's gone. No. Hello, YouTube. It's your boy. Make sure you subscribe, smash that like button, hit the bell button, all those good things. Please, can we edit this out, Adam? Oh, what am I doing? What a flippy joints. This is so cool. Where is everyone? How many? Do you want to take it? I've got the notes here. No, just come up and do it with me. Guys, we've got a guest on here. We got Fletcher. He's here. So Fletcher, tell me about tension.
Tension is basically just force.
Yep.
Some string.
Yep. So if we've got circular motion, and we've got the tension of the string, which is keeping our thing spinning around,
correct?
You know, like that. What formula are we going to use?
Can use the circular motion.
Circular motion formula. And what have we got for that?
NV squared on R.
And we're going to set that equal to our tension force. That's because in this case, our centripetal acceleration is represented by the tension force. And we've got all these answers, you know, we've got the velocity, we've got the radius, we've got the mass. So it's all a matter of shoving it in.
Shove it in.
And we get a very nice answer of 2.97. And remember, if we're going to use our unit method that we've been going before, we're going to end up with a very potentially strange formula, kilogram meters per second squared, which might not seem like force because we remember that force is measured in newtons. So this doesn't seem like force, but we can prove it to you that it is force if we look at F equals ma. We know mass is measured in kilograms, and we know acceleration is meters per second squared. So we have our unit of force being kilogram meters per second squared. So we could just cross that out and write newtons because it means the same thing, or we could leave it like that. And as always, we've checked our units and we've checked our significant figures, and we're good to go. All right.
That was lovely.
I'm gonna.
Yes.
I'll do this one. Friction on blocks suck, but we'll do it. So the trick with this question is making sure you're using the right angle for theta. So it tells you we've got a block sitting on a plane and its angle to the vertical can vary. So this angle that is this is the Greek letter phi. So it starts initially at 0. So it starts down here. And it moves up and up and up until it gets to this angle of 36.4. This angle here of 36.4. Cool? Degrees. We want, and that's when it's going to start to slide down. We want the coefficient of static friction for the block. So we're going to do what we do every time. I'm just going to redo them for you. We've got our weight force going straight down, because that always goes straight down. We then break our weight force into components. We have a component going down the plane and a component going perpendicular to the plane. And this is equal to our normal force. Remember, because our normal force is always perpendicular to the surface. So our weight force always goes straight down. Our normal force is always perpendicular to the surface, and we go from there. So remember, we want to figure out it's just starting to slide. So if it's just starting to slide, we can say that the frictional force is equal to the force, because we're going to have a frictional force coming back up the plane. Remember, frictional force goes always against direction of motion. So we've got a frictional force up the plane. Down the plane, we've got mg sine theta, with this being our angle theta. So I'm going to deal with theta, and at the end, we'll sub in phi. So we've got mg sine theta is equal to the frictional force. Now, it's good to remember that the frictional force is always the coefficient of static friction multiplied by the normal force. And in this case, based on our diagram, you should be able to see that our normal force is equal to the force down the plane. So we're going to end up with mg sine theta is equal to mu, our coefficient of static friction, multiplied by mg cosine of theta. Cool. Obviously, you should be seeing nice cancellation here, and we should end up with this probably well-known identity formula equation to you, where our coefficient of static friction is equal to the tangent of the angle of the plane. Cool. But the problem is we don't have theta, we have phi, but we know phi is equal to phi is equal to 90 minus theta, or in this case, theta is 90 minus phi, actually would be better. Apologies. Theta is 90 minus phi. So we pop that in, we can get mu is equal to tangent of 90 minus phi, which is 36.4 degrees. You can pop that into your calculator and you'll find a very sexy value of 1.36. Let's do always what we like to do in physics and take a reality check. Our coefficient of friction when it's like there's no friction is like, we call it 1. So anything that has friction is going to be higher than 1, which is great. We've got an answer 1.36. It's not 10 million, so it's not anything crazy number like that. So this seems to be plausible. And you can also remember that we've got that's the wrong thing. Go back. Three significant figures, and that it's a ratio, so there's no units for our coefficient of static friction. Sweet. Okay. Question 3 just requires you to have an understanding of what mechanical energy is and what conservative forces are. So remember, mechanical energy is our potential and our kinetic. It's all that, like, it's just the energy of the system, really. So we've got, when's it going to be conserved? If friction forces are absent, might be conserved. But if we imagine our block and we think in reality, if friction is absent, great, we've got conservation of energy, but there's still going to be air resistance there. That's going to be annoying. So it's not going to be conserved when just frictional forces are absent. Same goes for aerodynamic drag. You know, if that's absent in one instance, that might be true. So for example, a block falling through the air, that's true. Mechanical energy would be conserved, but it's not going to be generic enough. So we need, and we'll jump down to D for a reason that you'll see in a sec. If non-conservative forces do work, that's the same as non-conservative forces. We define work as Fs. So if we have a non-conservative work doing force, it exists, it's in the system. So that's also wrong. I don't know why I was ticking them and crossing them, leaving non-conservative forces are absent to be the only answer, which we should know to be true. If there's no non-conservative forces, we'll have a conservation of mechanical energy. That's the same with like your momentum. You'll have conservation of momentum if it's a closed system. All right. Oh my God, I've already just spoiled the next question. Momentum is not always conserved. It's conserved when non-conservative forces are absent also. Yeah. Cool. All right. So I'm gonna skip this question only in the interest of time, I think. Maybe I'll run through it very briefly. Okay, so we've got our kinetic energy. In this case, we've got our conservation of energy because we're neglecting air resistance. There's no other non-conservative forces. So we can say that at maximum height, our kinetic energy, our kinetic initial is equal to our final potential energy. So we're going to have 1.83 times 10 to the 1 is equal to mgh. M is given to us, G is a known constant. You'll only just need to convert your G. And you can find your H. Cool. The second part, you're going to want to use conservation of energy. So that your initial plus your kinetic initial, sorry, gravitational initial plus your kinetic initial is equal to your gravitational final plus kinetic final. And again, it's always good to just define however you'd like. So the way I defined it in mine is I said down here at the bottom of the cliff, I set that equal to 0 for my potential. So therefore, the potential I've got here is mgh, where h is the height of the cliff. So we're going to end up with mgh plus 18.3, because I've just converted our kinetic energy to get rid of that. That is going to be equal to our final potential energy is down here. So it's going to go up. We don't actually care about the up part because we're only interested in the beginning and the ending. So at the end, it's going to be 0. This is going to be 0. And our kinetic energy is, it tells you in the question, where does it say? So we need the speed to be twice what it was when it was thrown upwards. So 1/2 m u 2u squared. So you can calculate this initial velocity by just making this equal to 1/2 mu squared. And finding that, you plug that all in and you should get a value that you like for h. Sweet. Okay, moving on. A satellite of mass m. We've got a circular orbit around the equator of the Earth. Again, I'm not going to do the rote calculations, but I'll just show you the equation you got to use because there's an annoying trick in this question. So again, what do we love? We love diagrams in physics. So we've got the Earth here, we've got a satellite up here, cool, with some height and remember some radius of the Earth. We want the orbital velocity. So you should remember that the orbital velocity formula is given by root gm on r, where m is the mass of your central body and r is the radius from the center of the body. And g is a constant, so it's going to be g times the mass of the Earth divided by the radius of the Earth plus the height that it's at in meters. So 646 times 10 to the 3. Cool. So you've got to remember with this, capital M is the mass of our central body, and the radius is the complete radius, this distance here. So that's going to be the radius of the Earth and the height of the satellite. So that you should just be able to plug in. Those should be on your formula sheet, I believe. Oh, I shouldn't touch the mic. Okay. How long would there be between passes in hours of the satellite overhead for a given location on the equator per day? Neglecting the rotation of the Earth, thankfully, because that would be not fun to calculate. So we need to figure out what this question is actually asking us. So how long? So straight away you should be thinking time. It's good stuff. Anyway, you should be thinking about time. And the only sort of time we like is we deal with periods when we're looking at circular orbital velocity now. And in fact, this is just asking us for one period, because it's basically saying it's here. How long will it be between it passes back to that point, which is basically the period. So what's one period of the rotation? And the formula we're going to use again is T is equal to 2 pi r on V, with V being that we calculated before, and R being the same as this, the radius of the Earth plus the height of the satellite.
So yes, not a bad question. All right, simple harmonic motion. So this is another type of periodic motion. So it has periods. We're not moving in circles now. Springs, pendulums, all these sort of things use simple harmonic motion. I'm sure you've tackled this. I don't know why I'm explaining it to you again. We'll tackle the question. So, which of the following statements best describes the definition of simple harmonic motion? That's what we're doing, the definition. So, simple harmonic motion has an amplitude that does not decrease with time. That's not going to be true because we know that our simple harmonic motion is like that. So that's got a changing amplitude. All right. Simple harmonic motion is motion where the restoring force is inversely proportional to the displacement of an object from its equilibrium position. That's not true. This is because we know we've got a formula for our restoring force is negative kx, and this k is telling us that it is actually proportional. The other reason is because the restoring force is directed towards, which comes from this negative side. So, you know, if you pull a spring out, where's my spring, Fletcher? Right here. Ignore the fact that's probably a bit too complicated, but if you pull this springs out, the force is going to be proportional to how far you pull it and also directed back towards the opposite to the way I'm doing, which is why spring is back. So it's going to be an organ pipe. So that's our simple harmonic motion definition of it. All right, now we've got an organ pipe. Right, so what do? We draw it. Bang, bang. Let's see how badly I can draw. We've got, so it's saying 2 nodes within the pipe and it's open at both ends. So that means we know we're going to get antinodes at both ends. That's just kind of how we define it. And we're going to get 2 nodes along it. So maybe, oh my God, that's really good. I'm really happy with that. So yes. All right. Next, what is so we've drawn it here. We can write the length being 5.2 meters. All right. What is the wavelength of the standing wave? So this is a standing wave because that's what happens when we've got it's driving it to oscillate that. So we need to look at the wavelength. Remember, wavelength is like the distance between how long it takes, not how long, sorry, the distance that it takes to return to the same point, which, hey, if you look at that quite neatly, that's one wave. So our wavelength, lambda, is equal to the length of our pipe, 5.2 meters. It's quite nice. All right. If the speed of sound in air is 330 meters per second, what is the frequency that it's oscillating at? We've got a very nice formula, which is the velocity of a wave is equal to its frequency multiplied by its wavelength. So we've got 330 meters per second is equal to the frequency multiplied by 5.2 meters. Cancel. And hey, look, we've got frequency equal to 63. And we've got 2 significant figures. So it's 63 per second, 63 things per second, which is just 63 hertz, which is the unit that we use. All right. Moving on, we've got a pendulum. Yeah, I'll do this question and then I'll take a brief break because I would like to. So suck it. And then we'll come back. But this is all going to be edited out, so there's not going to be any break for you because you'll be doing online. If you do this, I hope you enjoy it. If you do, I hope you've been enjoying this so far. I think Adam might be there. This is so informal, but I'm enjoying it. And yeah, Fletcher's out there. That's exactly. All right, we got a simple pendulum. So it's always good to draw pendulums. That. I'm going to draw it on an angle because it's swinging. That. It's an angle from the vertical. All right. Pendulum is swinging back and forth. Simple harmonic motion. Calculate the period of this oscillation. I expect would have done. Why am I writing in red? Let's write in black. You probably did a experiment on this at some point. You've got a sexy formula. T is equal to 2 pi L on G. That's an L. L's like that. Cope. Shove it into the formula, and away you go. Pretty much 2 pi square root 2.5, and G we always define as 9.8, never 9.81, just use 9.8, always easiest. And you get our period of oscillation to be something I didn't calculate, so I'll do it for you right now. Times the square root of 2.5 on square root 3.17 seconds. Now you're probably screaming at this point because I've do this every time. Units and significant figures. Units and significant figures. Great. We're happy. Everyone's happy. Yep. Okay. So we've got that, but now the pendulum is stopped. So note the non-dependency on mass. You could have, I mean, this is quite a heavy pendulum. You could have a really light pendulum, and it will still have the same period of oscillation, because we're assuming it's going in simple harmonic motion, so we're ignoring the effects of air resistance. That sort of stuff. Cool. Second part, pendulum is stopped, and we now get a spring. The mass is set oscillating on this spring, and the oscillation is observed to have a frequency. So we've got the spring here, and we've got mass, and it's going up and down. Cool. And the oscillation is observed to have a frequency of 0.735 hertz. What is the spring constant? Well, we're going to use, again, the very nice formula. Omega is equal to 2 pi f, and omega squared, or omega in this case, is equal to the square root of k on m, where k is our spring constant. So you can go through the motions, do this question, and we're going to end up with k being 4 pi squared f squared multiplied by m, which when you put into your calculator, you will get f, we said, was 0.735 hertz, and our mass was 16.9 kilograms. You should get k being equal to 360. And just like our coefficient of static friction, we don't have a unit for this. No, sorry. I think we should have. Yeah, sorry. And it's newtons per meter. So, we do have a unit. Cool. So these formulas, like the relation omega squared on is equal to k divided by m, is quite a nice one to just have in your back pocket. I think it might be on your formula sheet. If it's not, keep an eye on that. And also the fact that omega is equal to 2 pi f. Cool. All right. I'm going to take a short break, and then we'll be back. Want a break from the ads? Thank you for joining us for this first hour. We'll be back shortly to discuss, would you believe it, electromagnetic waves. Hang in there. Yeah, round of applause. Thank you. So we've got, how is the magnetic field of an EM wave oriented with respect to the direction of the travel of the wave? Mouthful. We'll just draw an EM wave traveling through time. We'll call this our, kind of, that's the way it travels through time. It's going to go like, this is going to be our thing. And then we've also got another one kind of going out like this. And it's very hard to kind of imagine it, but you should know they are traveling perpendicular. So they're all three perpendicular. So we've got the EM wave, the magnetic wave, and then it travels that way. And they're all three perpendicular to each other. So that's the next question. In unpolarized light, are you here for the fundamentals? Yeah. Please take a seat. Yes. we're about halfway through, but we'll probably put the first half up on YouTube. So yes. Cool. So yes, as I was saying, we've got our electric wave, our magnetic wave, and that travels through time also perpendicularly. The trick of this question is that it's saying in unpolarized light, but we've got to remember with unpolarized light, that just means these are all on different angles to each other, but still the fields are still perpendicular to each other. They're always going to be perpendicular to each other. Cool. The next one is, can an electromagnetic wave travel in a vacuum? This is that, I mean, the answer is yes. This is because electromagnetic waves are not mechanical waves. They don't require a medium to move through. They still move, obviously in like the, air here, we've got electromagnetic waves going around, but they can travel in a vacuum and they don't require a medium to propagate through. So that one's yes. Cool. Can you see from back there? Okay. All right, cool. So we'll tackle question 2. We've got a silicon crystal. We can just draw it out, sort of thing. It's just really gonna look like this. It'll be 3D though, sort of thing. Anyway, cool. So, and it's saying that the distance is what we call an 2.35 angstroms, which is just this quite small distance there. So all this question is really asking us is to understand atomic distances and how to manipulate them, and also how to deal with a little bit of light and frequency stuff. So we're just going to work through it slowly. So we've got, how much larger is the wavelength of visible light with a frequency of this? And it wants it as a ratio of the wavelength to the atomic distance. So this is where we're aiming. We're aiming to get A over lambda. We've already got A, that's given to us here. So we've got to work out lambda. We're told F is equal to 5.35 times 10 to the 14 hertz. Cool. And we know the formula, V is equal to F times lambda, where this is the speed of our wave is equal to its frequency multiplied by its wavelength. Cool. And it's visible light, and we know light always travels at the speed c. So you can set c equal to that. So we wanted to find lambda, our wavelength. So we've got lambda is equal to c divided by f. And if we pop that into our calculators, you should get some very small number. We'll call it 5.61 times 10 to the 7 meters. And as I've been saying all day, we've got three significant figures, and we've got it in SI units of meters. So I'm happy with our answer for our wavelength there. Cool. And next step was to actually calculate our ratio. So whatever we'll call it, our ratio is equal to A over lambda. A is 2.35 angstrom, so 2.35 times 10 to the minus 10, given to us there again, meters, divided by 5.61 times 10 to the 7 meters. This is quite nice. Our units are canceling off, which is what we want, because this is just a ratio. It should just be a number. It shouldn't really have any units attached to it. It's like our coefficients of friction. There's no units attached to it. And when we put this one into our calculator, we should be getting 4.19 times 10 to the minus 18. 3 significant figures and no units, which is what we want. Happy? Good. Cool. All right. Now, Annoyingly, this is split over 2 pages. So if you want to take a second to draw down this diagram, I will pop all the information on from mine. So we've got, oh, what is that? N1 is equal to 1. So the refractive index of our air is equal to that. N2, or our oil, is equal to 1.46. And N3, our water, is equal to 1.33. Cool. That's our first bit of information. We also know that this angle is equal to 10.4 degrees. This is I'll show you this to you later. It tells us down here our oil is 1 millimeter thick, which I'm just going to call 1 times 10 to the minus 3 meters, because we always want to deal with our SI units. And I suppose we'll call this theta 2. That's our diffraction angle. That's our refraction. And that's our theta 3. Our second refraction angle. Cool. Now, this is all the information here for you. So it wants the final angle of the ray of light in water and the displacement d. So I'll just pop back to the diagram. So it wants the final angle, theta 3. So the two things we need to find, firstly, is theta 3. And secondly, it wants the displacement d. So this is a 2-step part question. Just to fully explain what's happening here, our ray of light is coming in. When light changes medium, we know it refracts. Some of it will reflect, but we only care about the refracting part. That bends on an angle towards the horizontal because the refractive index is higher. Of the second medium, it's a higher refractive index, so it bends towards. Then as it passes through the water, it's again a change of medium. It's going to refract again. It's a lower refractive index, so it's going to bend back out away from the norm. And that's how we're going to get these. That's what's happening here. This dotted line here is just the continuation. So if this line continued through, that's all that's giving us there. But I'll get rid of that because we don't need these lines. Cool. Okay, theta 3 is more on the simpler side. We have a very neat equation called Snell's law, where N1 sine theta 1 is equal to N2 sine theta 2. Cool. And our 1 and 2 just refers to any two different media. So we don't need to bother calculating what happens with our oil or what happens there. We can just jump straight to our air and our water. Mathematically, that's because if we did take N1 and N2, we calculate our theta 2 angle. And then we could go a step further and then go N2 sine theta 2 is equal to N3 sine theta 3. But that just gives us the equality N3 like this. So we don't actually need to calculate the middle step. It's superfluous, not necessary. So we're going to omit it because we want to take as many shortcuts as we can, because we want to save time, make sure we can get to as many questions as possible. Cool. So thankfully, Snell's law isn't too difficult to plug and play. We've got our first refractive index of 1 and our first angle of 10.4 degrees given to us. And remember, we're just jumping straight to our water. That's multiplied by 1.33 sine theta 3, which is what we want to calculate. Cool. You can go through the motions yourself if you'd like, but I'll just tell you that theta 3 is equal to 7.8 degrees. So what's happening is our light is bending towards the normal and then a little bit back away. And this angle down here is 7.8 degrees. Cool. I'm happy with that. We next need to calculate this distance here, d, which requires a few steps. unfortunately, it's not as simple. The simplest way I thought about doing it, I'm going to zoom as much in as I can. And we're going to use a little bit of trig. So we've got 3 triangles here. Two triangles here. 1 and 2. And my thought was to find just this line here, which I'll do in this color. Oh my, that's massive. Please say this is small. Yeah, there we go. To find just that distance there, D, that we want, we calculate the entire length and subtract off just that small bit there. So that's my approach to this. I think that's probably going to be the easiest way to do that. So what it might be worth doing is just redrawing our 2 triangles to make it simpler, and we don't have to deal with this tiny thing here. So we've got, this will be our first triangle in red, and this will be our second triangle in blue. So this is our first triangle here, 1. So triangle 1 is this angle, like this is going to show this angle is equal to that angle. So we're going to have 10.4 degrees in here. This is a right angle triangle. And the side we're interested in is down here. So we'll call this, we'll call it X. Yeah, X, whatever. It doesn't really matter. And what we can do, so that'll be our first triangle. We'll draw our second triangle now. And our second triangle is our smaller triangle. So that's got a different angle. And that angle is actually going to be, I've drawn too much stuff here, so it might be a bit difficult to see. But that's our smaller blue triangle, this one. And that is that angle there. And that angle is going to be our θ2 refracted angle. Okay. So our big triangle is our non-refracted ray, because that's what it's telling us, that this dotted line is that. Our smaller triangle is going to give us our refracted ray, θ2. Now, I'm just going to pop θ2 in there for the moment. θ2 in there. And now this is our little small, so we'll call this y. Matter, we're just going to give it 2 names. So we need to work out these 2 distances, do a little basic algebra, and then we'll get our answer. Let's first calculate what θ2 is. We're going to reapply Snell's law. This part, Snell's law, we're going to go 1 sine of 10.4 degrees. Because remember, 10.4 is our air first angle. That is equal to 1.46, because now we're interested in this diffraction angle there. So it's going to be our 1.46 by sine θ2. Cool. So we should be getting that θ2. Does this equation make sense? Perfect. Just shout at me if it's not making sense. I promise I'll take it back and explain it. This is 7.102 ... It's always good to try keep your answer not round until the end. So I generally keep it in my calculator. So it's fine to write it like this. Great. And so now we should just be able to apply a bit of basic trig. And we can go. We want to use here. Sorry, the last part we need one more value on here. Remember, we're told our oil film is 1 millimeter thick. So this is 1 millimeter and this is 1 millimeter. Cool. So we can use the tangent function here. So tan of 10.4 degrees is equal to opposite over adjacent. Sorry, I do a lot of tutoring for year 10 students, so I say it all the time. So, and then 1 times 10 to the minus 3. So we can find our x value there, and we're going to get x of a very nice, you know what, I'll just calculate it. 10. You know, I'm actually going to leave it in millimeters because that just might be easier. So remember, we can leave stuff in millimeters, like with different SI units, as long as we're not using any proper equations. So if we're using this equation, we'd need to get it in SI units. But if we're just looking at ratios or trig stuff, we can keep our units. So I'm going to leave this as 0.184 millimeters. That's our X. And then our tan of theta2, which we defined was 7.102 ... degrees, 120, is equal to Y over, again, the same 1 millimeter. So we're going to get that this is 7.102. So Y is equal to 0.125 millimeters. Returning to our graph, finally, hopefully we could see that we should be getting our full length, which we said was X on the big triangle. X minus Y, our small length, should be equal to D. I'll keep that there. X minus Y is equal to D. Therefore, D is equal to 0.0594 millimeters. Cool. If you wanted to get this into SI units, which you could, you just multiply by 10 to the minus 3. So that would become, you'd have a whole bunch of zeros. So then I'd probably turn it into like scientific notation. So I would call that 5.94 times 10 to the 5 meters. So, and that's probably a good place to stop there with that distance there. Also always nice, let's do like a reality check. We're dealing with millimeters, so we know this is going to be very small. And we know that our change of angle is like, it's only like 3 degrees difference, 10.4 degrees versus 7 degrees. So this little distance there is only going to be marginally small, which is what we got. Whew, I'm happy with that. Are we happy with that? Good to hear. Too easy. Let's move on and do some electromagnetism. So we're considering our charged metallic sphere. Where are the charges located? So what happens when we have full, like, you know, not what am I thinking, like things with a density of sphere and they're charged, the charges always reside on the surface. So it's not going to be in the center of the sphere. It's not going to be uniformly distributed throughout the sphere. It's actually going to be at the surface with a uniform distribution. That's because we're assuming our metallic sphere is also uniform. If our sphere had holes in it, stuff like that, we would have a different distribution. But because it's a sphere, all the charges are going to repel and they're just going to sit on the outside of the sphere. Cool. And our charged solid metallic sphere, the electric field lines are always going to be perpendicular to the surface. They're always going to push out from the sphere, basically. Cool. That's all we have on that one. All right. That was pretty simple. I'm going to skip this one and come back to it, only because it's a little bit of a trek and I kind of don't want to do it now. We'll start with this one. So we'll have a look at our diagram before we do anything. So we've got an electron is accelerated. So we've got our electron here. It's moving up through what we call these parallel plates. So it's going to, you know, a capacitor, it's going to boost it up. It's going to give it some potential difference, some acceleration by the time it reaches here. Then it's going to hit a magnetic field. Now we can use our right-hand rule to work out, to verify that this is the way it's going to move. We know they move in circles in magnetic fields, but we use our right hand, we've got an electron, so we flip the direction of motion. So a proton would be going up, that electron's going down. The magnetic field is into the page. Therefore, we're going to get that our force pushes to the right and that goes radially around, causing this very nice circle, which we can agree with. Always good to just check that we're agreeing with the diagram. Cool. Sweet. So we're given our voltage, not our velocity, our voltage, and we're given the radius of our circle. So we've got to do a few things. We have to calculate the kinetic energy of our electron. So we've got this formula, which work is equal to QV. Effectively that when a charge is in an electric field with a voltage, there's work done on it. We also know that in this case, the work is going to be equal to the kinetic energy by the work kinetic energy theorem. So we've got this relation here. And now this is going to help us work out our kinetic energy. Q is our charge. Our charge is a single electron. So this will be on your formula sheet if you haven't got it in your head. 1.602 times 10 to the minus 19. Technically, this should be negative, but we're looking at energy. So the negative sign is kind of like absorbed, given, it doesn't really matter as much. You could keep it there if you'd like, but it's more just to show, you know, it's always important to remember it. So we've got that. That's our charge done. We need our voltage. Hey presto, our voltage is given to us, 4569 volts. Don't forget that joule, our charge is measured in coulombs. And we've just shown that, you know, we can show here that coulomb volts is a measure of energy, giving us overall a value of 7.32 times 10 to the minus 16 joules. And that is our kinetic energy of our electron. Cool. All right, now, what magnetic field strength is required to ensure that the electron hits the detector? So we need to, so if we return here, we've got our electron comes up. Our electron comes up, gets some speed, and then shoots around. So we need to work out that speed of our electron. We're going to need to work out our speed because we need to think of an equation that involves our magnetic field. The easiest one to use in this case, because we don't have currents, we don't have wires or anything like that. So we've got F is equal to QVB. Cool. That's our formula. And we know, we can see it here, or we know that our magnetic field causes radial circular movement. So we can equate this to mv squared on R, which is our centripetal force equation. So effectively what we're showing here is we've got something that involves our magnetic field strength. We've got our radius, which is given to us in the question. We've got our velocity, which we're going to need to work out. And we've got our charge, which we know. And so this looks like a nice equation that I'm pretty happy using. Let's do a little bit of simplification. We've got velocity on one side and a squared there. And we'll just isolate it. So we can say the magnetic field is mv on QR. You've probably derived this at some point in your lectures or in your homework, hopefully. It's a nice little relation showing when you've got things moving, you can work out the magnetic field strength to make it move in that circle. So, as I said, M is known, Q is known, R is given to us. We're stuck with V, but we're not really, because what did we just work out? The kinetic energy. And we know the kinetic energy should be equal to 1/2 mv squared. So, instead of substituting this in and dealing with a whole bunch of annoying stuff, I'm just going to calculate our velocity. So what we'd do is we'd bring the 2 up, we'd divide by the mass, and then we'd square root it. We end up with our velocity being 0.4 times 10 to the 8 meters per second. As I've said before, we can reality check. This makes sense. This is relatively close to the speed of light, and electrons, you know, when they get accelerated, this is quite a large potential. So it's going to accelerate it quite quickly. It's going to get pretty bloody fast. And so that's giving us that there. Good to go. We'll pop this into our equation. So the mass of an electron is 9.109 times 10 to the minus 31. Our velocity is 0.4 times 10 to the 8. We're dividing that by our charge, 1.602 times 10 to the minus 19, and our radius, which is 8.5 centimeters. So we've got to get that into meters. Cool. I'm not going to bother with the whole unit thing because it's not really going to yield us anything interesting here. But this value, when you plug it into your calculator, gives you quite a nice value of 2.68 milliteslas. So yeah, if you want, you can pop that into your calculator, check me, but that's what you should get. Again, we can it's a bit harder to reality check this because we don't as much deal with this in reality all the time. But it's not going very far. It's moving pretty fast. So this is, kind of a plausible answer. If we had something crazy like a humongous magnetic field or a very small magnetic field, I'd get a little bit worried, but this is quite nice. All right. So, cool. We're going to repeat that experiment for a helium ion. So now we've got a lot more mass, quite a bit more mass, because electrons weigh next to nothing. And protons and neutrons, we know, actually do weigh quite a bit. So we need to work out the potential to reach the same velocity as the electron before. We can just do the exact same calculation. QV is equal to 1/2 m lowercase v squared. Cool. So we want the potential. So we want this. That's what we want. We know that our V is going to be the same as that V because it told us the same velocity. We know our mass should be, we can work out by looking at the formula sheet because it tells us 2 protons, 2 neutrons, and 1 electron. So we know the mass of a proton on the formula sheet. We know the mass of a neutron on the formula sheet, and we know an electron. So we just would sum them all together, leaving us only with Q. So you might be tempted to go, the charge is 2 protons and an electron. So is the charge, like, we just need to think about relative charge effectively. So if we just treat a proton as +1, and an electron as -1, and a neutron as 0, we can literally go 1 + 1 for our 2 protons, +0 for our +0 for our 2 neutrons, -1 for our electron, giving us just 1 overall charge. So the overall charge of our helium ion is 1 elemental charge, which is just the charge of 1 proton. Again, 2 protons, 1 electron, you can think they cancel each other out. So we've got 1.602 times 10 to the -19 coulombs. And that is our charge. We can shove that into this equation. I'm not going to go do this because I can't remember the mass of protons and neutrons off the top of my head. I think it's -2. Anyway, but this is the formula you want to use. And the trick with the question is getting the mass correct and getting the charge correct. The last part is if the electric field needs to be inverted, give a negative answer. Remember, our field currently accelerates an electron this way, so a negative particle that way. So it's going to, if we wanted it to accelerate a positive particle that way, we would need to flip it. Because currently on this, a negative particle goes that way, so a positive particle is going to go that way. But we want our positive particle to go the other way, so we would need to invert it. Cool. So we would need to be giving a negative answer overall. And then basically you're just going to go through the same thing for the next one. We've got a magnetic field required for the helium ion to hit the detector. We're going to use B is mv on QR again, using the same m from this equation, the same q from this equation, v from before, and r from before also. Again, the last part, does the magnetic field need to be inverted? Let's think about this. Using the right-hand rule, if we just look at the sort of entry point here, it's a positive charge, so it's traveling, we'll call it up. The magnetic field currently is into the page. So using our right-hand rule, our force is going to be outwards. So basically that would cause our proton to travel that way. So we want to invert it. If we invert our magnetic field, have it coming out of the page, then we'd get the right direction. So we also are going to have a negative number there. Cool. I hope that made sense. Plugging it into the equation is simply just, make sure you plug it into your calculator right. There's not too much I can teach you there. So yes. Cool. Any questions? Making enough sense? Perfect. Cool. Last one is reasonably simple. We've got two parallel wires experience their force. Current is flowing in both the wires. You might have done this experiment in class. We've got our two wires there. Is the force a retractive or repulsive if both currents flow in opposite directions? Two ways to approach the question. The first way is memorize. You can just know that if it flows in opposite directions, it's going to repel. If you don't want to remember that and want to think about it, we can use our right-hand curl rule. So let's say we've got our current flowing in opposite directions. So let's say one current goes that way, one current goes that way. Let's deal with our left-hand side first. So our magnetic field is going to come out radially from it. So if we use our right-hand rule, the current's going down. So on the left side of the wire, it's going to be going into the page. And on the right-hand side of the wire, it's going to be coming out of the page, out of the page, out of the page, out of the page. If we deal with our right-hand current, it's going up the page. This is coming out of the page, out of the page, out of the page. And on the other side, into the page, into the page, into the page. Cool. So these two magnetic fields are going to repel each other because they're traveling in the same direction. So they're going to repel. So we're going to have repulsive there. If they were opposite, they would add together and attract, but they're going to repel. Cool. All right. Our last one, in which case is EMF not induced? Give me one sec.
Nancy, Ari, there's like there should be like a green light on the wall. Do you see it?
Yeah.
Okay, so it's just that.
Okay, cool. In which case is EMF not induced? So there is a change in the area of the coil in a constant magnetic field, and the area is perpendicular. So remember, we have our EMF is negative delta phi over delta t, but we have phi being BA. So if we have a change in area, we're going to get an EMF. A coil is rotated. So if it's rotating, we are not necessarily going to get any change in these. If it's moving, we might, but if it's rotating, we might not. Let's look at the other ones. So let's put a question mark here. This might be right. There's a change in area of the coil in the constant magnetic field, and the magnetic field is in the direction of the plane of the area of the coil. So we've got so if our coil is sitting here and our magnetic field comes down on top of it in the first part, we're going to get it's perpendicular, so we're going to get a change. But if our area of our coil is in the direction of the plane, yeah, it should Fletcher, actually, no. Which one this is coming? In which case, it's an EMF not induced. Coil is rotated. If it's rotated, it shouldn't induce EMF, right?
Rotated, no, it shouldn't.
Yeah, but then this one is like in the magnetic field is in the direction of the plane of the area. This will, they shouldn't, I don't think. But it's in the direction of the plane. This will, yeah, and the last one definitely will. Yeah. Cool.
Yeah.
So yeah, B. A will cause it because we've got a changing area. B might not. C will change it because we've got a changing area. And D is our coil with a constant area, our changing magnitude of B. So it's going to be B. All right, and then the last one, the polarity of the EMF. Well, Ampere's law is not related to EMF, so it's going to be Lenz's law. Lenz's law states that the direction of the EMF will be opposite to the magnetic, the direction of motion. So that's going to be Lenz's law. That brings us to the end. There's no one on the Zoom. Do you have any specific questions you want me to tackle or something you'd like me to go over or explain or anything? Right hand rule, yeah, certainly. Cool. So with our right hand rule, we're just gonna discuss. There's two different types. I'm actually not gonna use the board. I don't really need to. So our right hand rule, we've got two different types. We've got what we call the right hand push rule, which is where you use a flat palm, and the curl rule. The push rule you're always going to use when you're dealing with forces or Lenz's law or anything like that. When there's three sort of things, you're always going to have your direction of motion from your thumb. You're going to have the direction of your magnetic field from your fingers, and your palm is going to be the force. Cool. So I'll explain that again. We've got, actually, we'll use the board. I'll use a diagram. Let's say we've got a magnetic field into the page, and we've got a positive charge moving to the right. So we get our right hand, always our right hand. Now, I always start with the direction of motion. So you get your thumb as the direction of motion. So the thumb in this case is going to the right. I'll do it your direction. The thumb is going to the right, okay? The magnetic field is into the page. So my fingers are pointing into the page. Yep, so like that, into the page. And then my palm is like the consequence. My palm is showing me the force is going to push it upwards. Make sense? Direction of motion, magnetic field, force. Cool. If you've got a negative particle, there are two options. Either you use your left hand or you flip the direction of motion. I always prefer flipping it because that keeps you safe. If you always use your right hand and just remember to flip, it's easier than dealing with both hands. If you think you'd prefer using your left hand, go for that sort of thing. But I think I think flipping is probably better. Right hand push rule is for any time you've got forces. If you're dealing with Lenz's law, so let's imagine a coil here, and we've got a magnet dropping down. So this is going to help us with basically, sorry, if you've ever got curved things, you're always going to be using the curl. So in this case, the first case, we don't have anything curved here. Yes, technically, like the force will make it curve, but we're just looking at forces in this case. When we've got anything curved, wires, so for example, like wires, if we've got a current traveling through this wire, you know that the magnetic field is going to come like outwards around the wire, right? Yes? Yep, cool. So the way we can work that out is by using our curl rule. Thumb, so for the right hand push rule, it's very set. Direction of motion, magnetic field, force. The curl rule is not set. The thumb is something that's straight. The curved fingers is something that's curved. In this case, the straight thing is our current. Our current is going up, on the one on the right. Our current's going up. Our magnetic field is curved around it. So our magnetic field is our fingers there. That's the curl. In this case, we've got a curled wire. So our magnetic field is going to be up or down. So we can tackle this with Lenz's law. So let's say this magnet is dropping through this coil of wire. Have you seen questions sort of like this? Yeah, this is a pretty typical Lenz's law question. They can be quite difficult. So we've got our magnet dropping down. Faraday's law says a changing magnetic field is going to cause an EMF. We're going to have an EMF induced as a current in this coil. We need to work out which direction this current is, if it's this way around or the other way around. We don't know. But we can work that out. So there's a north pole dropping down. So the way I think about it is there's an increasing north pole into here. Lenz's law says we want to stop combat the direction of motion. So instead of helping this fall through by if we put a south pole here, it's going to attract it. It's going to move it down quicker. So what we actually want to do is put a north pole here, because this is going to combat, it's going to push it further back up push it up, it's going to like slow the rate of fall. It's combating the direction of motion. So we're going to get a north pole. The way the current is going to go is such that there's a north pole there. So our curl rule, if you're using anything, it's pointing in the direction of north. So it curls in the direction of north. This points in the direction of north. So we want to put a north pole there. So I put my fingers up because it wants to combat the north with another north. And so if I was looking from above, it's going to be going anti-clockwise. So our things are actually going to be going the direction I've drawn, that way around. So I'll like run through it again now that you've got it primed. We've got our north pole dropping down. We're going to have an EMF induced here by Lenz's law. That EMF is going to be, the direction of it is such that our magnet needs to be slowed down. We want to slow down because that's what Lenz's law says, slow down the direction of motion of our change. Our change is we've got a new north magnetic field dropping through. There's that change there. So to slow that down, we want to put a north pole right there in our magnet to like repel it, push it back up. We use the curl law because we've got something curved and we've got a magnetic field, or a current, in this case, it's a magnetic field. So we want our north, which is our thumb, to be upwards, not our north down. Because if our north is down, we'd be putting a south pole here, and that would be attracting. So we put our north pole there, and therefore, if we look from above, like where the magnet's dropping, we can see it's traveling anti-clockwise. Does that make sense? Happy with that? Cool. We can continue this question and think about, okay, great, it's dropped through. We've induced a north pole there. Now, it's dropped through. It's still south and north there. Now it's dropped through. Is this current going to change? Is it going to go in the same direction? Let's think about this. Firstly, do we have something to induce an EMF? Yes, we've got a change of our magnetic field. It's going to decrease as the magnet moves further away. We've got a decreasing south field. So we've got an EMF. Lenz's law, the direction is going to slow the direction of motion. The direction of motion is down and it's accelerating downwards just by gravity. So we want to attract it back up, right? Makes sense? So if we want to attract a south pole, what do we want to put in our thing? I've just drawn it there, but we want to put a north pole there to attract it back up. Cool. So we've still got a north pole there. Sorry, we've got a north pole facing downwards now. So our current is actually going to change directions and go the other way because we want a north pole at the bottom to attract our pole back up. So what you'll actually see is that your induced current, if you measured it, did you do this as an experiment? You might have. Anyway, if you do it, it's going to go like this. It's going to spike and then drop all the way back down and then spike. Kind of looks a bit like a heartbeat or something, I guess. Because we're going to have our induced current and then it's going to change the direction as the magnet drops through. So at this point, this is when the magnet is exactly in the middle. And then as it drops through Lenz's law, it's going to induce a current and then pop back up. Cool. So summary, right-hand rule, always when you've got specifics, when you've got a force, when you've got direction of motion, when you've got a magnetic field. Motion, field, force, perpendicular, always like that. Curl rule is when you've got something curved and you've got something straight. The curved thing could be a wire. The curved thing could be the current. The curved thing could be the magnetic field. Any of those things, that's what it is, sort of thing. That's what you use it for. Remember, this is north, this is south. So points in the direction of north because that's the way we draw our field lines, in the direction. Happy enough? Lenz's law sucks. It was my least favorite part of year 12 and my least favorite part of 1B. But it's not too crazy. You just break, with any physics problem, break it down into steps, tackle it one by one, and you should be good. Any other questions? Perfect. I think that brings us to the end. I will, just for us, if you don't mind,